In this recording, I'll be talking about the budget, token budget that we can set as guardrail. So this enforcement helps to prevent budget runaways and helps to make sure that the tokens the token budget is within the allocated budget. So here, as you can see, specific token budget is allocated, which is around 200 tokens in one case and 5000 tokens in other case. So the case in which the budget is allocated as 200, we will be observing that we will be running out of the tokens soon. And once in another case where the budget is 5000, we'll be seeing successful implementation of that. So if I execute this, I just executed this, and once we go to LangSmith, we can see the run where the budget was within the so this is the happy path scenario where the budget was 5000, and as you can see, the only 1665 tokens were burned out of the maximum 5000 tokens that were allocated, and the job got successfully executed. So the trace was successfully executed from end to end. So this is a happy path scenario, and let's see the other path. So here is another scenario when we only allocated 200 budgets, as you just saw in the code, and the code execution, the code run, the trace run exceeded 200 tokens, and it resulted in aborted since the tokens were exceeding the maximum allocated tokens. So in this case, the job got errored out, and you can see that that in LangSmith, that's the reason why the job got errored out. So this is another case when we can set budget token budget as well as latency budget, so that it can be traced in LangSmith as to what is the real reason behind the trace being failed. So observability helps to capture those scenarios as well. The next scenario would be talking about is stateful memory. That means when we go to observe LangSmith, we can see how the context is getting preserved between multiple turns. So each turn provides a specific context, and the next turn provides more context, and the next turn provides additional context. So there are 3 turns which keeps on adding context to the turns that added context earlier. So in this scenario, a turn at the first context, in which case it says, my name is Mohan, I'm a product manager interested in AI companies. I live in Irvine, California. In the second one, we provided the same we provided additional details. For example, the second turn says, what is the weather? In the second turn, we asked what is the weather where I live, and asked OpenAI to look up for the weather. And in the third turn, we asked specific question based on what you told me about OpenAI, calculate how old the company is, blah blah blah. We added additional information to the turn. So what happens is, when we started the context, so the context keep on adding additional data that we provided in each turn, and we can observe that in LangSmith as well. So I ran this, and we can see this similar observation as to how the context is preserved between multiple turns. So in this case, as you can see, the first turn the tokens were 213 tokens. The second turn 1 plus turn 2 context is added and sent to the ChatGPT, and that's why we see additional tokens. In the third that the context gets added from the previous two turns, and that's why you can see that the cost of the token count increased. So if we go into the details, you can see here that turn 3 has the turn 1, turn 2, as well as turn 3. So all the details of the previous turns were added to the context window and passed on to ChatGPT. So during the last turn, it remembered what was the data in each of the turn, and along with that data, if something was asked, it preserved the context and it said, for example, you see the output of this. It remembered that in the first turn, my name was given as context, and it remembered that and it displayed that, and with a statement saying your name is Mohan. And also in the turn 2, we pass certain information which it preserved and displayed in turn 3. So the context is stateful, and the turns help, and this can be traced in LangSmith as to how and what data is getting passed between each turns, especially from a context window standpoint, and we can also see how the context size is getting increased as the turns as the data as the context window is getting increased. So that's another benefit of LangSmith. The last one, the next step, next concept that I want to explain was how multi-step workflow with state graph. So in LangSmith, we can observe how the workflow is getting executed, whether it's parallel or sequential. For example, in this context, there are multiple nodes that are getting executed. For example, in this run, I can see each node does a specific job. For example, a node called classify intent classifies the intent. A research node does some research, does compare both, and then summarize, and then quality check, and then display that. So these steps are executed twice, as you can see here, and these are executed parallelly, and the sequence of the steps can be monitored in LangSmith. For example, if you go to the next run, you can see the quality score. Yeah, so these are the order in which the trace can be found. For example, you can see here how LangSmith is calling model, and the model is calling ChatGPT, and what sequence and what ChatGPT is passing back, and in what order. So that gives us a better perspective of the sequence of the calls that are being made. For example, here 4 tools are getting called by the model. Four tools are getting invoked with parameters which the ChatGPT is passing back to the agent, and the agent is invoking those tools with those parameters. So the order calls are being made are parallel, and that can be viewed in LangSmith. You see the runs. So So these are the sequence in which the these tools are getting executed one by one parallelly. So this eliminates the runtime, since each of those tools are getting executed with 1 second. And now as you can see, total like 2 seconds is a runtime, as opposed to when getting executed sequentially, which could take 4 seconds. So this is how we can check in LangSmith whether the tools are getting the order in which the tools are getting executed. Let me show you one more. Show all collapse. Yeah, tool 1, tool 2, tool 3, tool 4. So each of these tools are getting executed sequentially, parallelly, and each of them is taking 1 second. And you can see first tool is getting called with show weather San Francisco, slow weather Irvine, same thing with different parameters. And as you can see, these are getting executed sequentially with 1 second runtime for each. And then finally the agent gets the data from each of these tools, summarizes the data, does the quality check, and then responds back to the user with this final output: the weather in these cities are blah blah blah. And in the final summary step, what the agent did is basically returned back the response it got back from LLM, that Austin is the hottest city with temperature of 89 degrees. So the agent consolidated the responses it got back from ChatGPT's GPT, and then finally consolidated and displayed the response here. So that's the advantage of using Lang observability tool like LangSmith, so that we can see how the traces can be monitored, and how the runs within those traces. For each execution, there is a trace that, and within those traces there are multiple runs. So if and this helps to like see like from a more granular level what's happening in each of the run, at what step do we have an issue, how many tokens are getting consumed in each run, and what is the latency of that run. And if there's a bottleneck at that run, how can we mitigate that? Is it a system issue, is it a user issue, or is it a process issue, or is it a spec issue? So those issues, those kind of analysis can be done by using LangSmith. So let me see if I covered all the scenarios. And then this is what I was trying to say, like this run basically captures the flow and then finally summarizes and displays that. Parallel tool execution, I mentioned about that, how uh, multiple calls can be invoked parallelly. And the beauty of the observable tool is we can see that all that happening is in a graphical format, connected by in a graphical representation in during the runs and traces. And finally, there's a provision in LangSmith where LangSmith can send the details uh, for all the traces and all the runs, how they performed for the day. For example, in this case, I asked LangSmith to provide me all the jobs, all the traces that were successful, all the runs that were successful, and it gave me a detailed report like total runs 50, the success rate was 98, failed run was 1, and average latency, maximum latency, tokens consumed, average cost, and also gave me a detailed report of those that exceed say 10 seconds, that has 10 seconds latency, or the run that has more than consumed more than 3000 tokens. So and the other thing is, for if you take any trace. And if you go to evaluators, not you, we can do multiple tracing and monitoring. Yeah, we can check all the how the we can also monitor the golden SLAs. For example, P95, P50. So these golden SLAs helps us to see how the runs are performing in terms of latency. For example, P50 here says 5.2.94 and P99 says 5.21. So these are the golden SLAs. P50 meaning that for 50% of P50 of 2.94, meaning that if there are 100 runs that are getting executed, we can guarantee 50% of those runs or 50 of those runs to be below 2.94 seconds. Um, and P99 means we are guaranteeing that if there are 100 jobs that are run, 100 runs that are happening, then 99 of those runs will have a latency of less than 5.21. So these are the golden SLAs, especially from a latency standpoint. So we can see that, say for example, today there is no run, but yesterday how our P99 and how our P50 values are, so that we can compare them against our golden SLAs, whether we are meeting our client SLAs. um, for example, in some specific scenarios, the P50 the golden SLA would be 3, and P99 say 6 seconds. So in this case, we are good because both P99 and P50 are less than 6 and 3 seconds. We are good on that aspect. So we can do that on a day-to-day basis. We can monitor that in LangSmith, how the latency trend is occurring on a day-to-day basis, whether there are any spikes that are occurring. Yeah, so there are a lot of other things that can be checked. For example, tokens and costs. We can check what are the number of tokens, what is the cost that occurred on a day-to-day basis, whether it's spiking, whether we are running out of the token budget on a specific day, or latency budget are exceeding or maintaining the latency budget, as I spoke earlier about by talking about P50 and P99. And also LLM latency. So we can also check the hardness and LLM's latency. So we can isolate where the issue is, whether the latency issue is due to the harness issue, or the issue is due to LLM latency. The harness are everything but except the LLM. The harness could be the orchestrating agent. The harness could be the edges that are connecting two nodes. The harness could be anything that is not LLM related. Could be anything, right? But if the overall latency is getting slower, we can isolate the problem, like where the problem is occurring, whether it is in the harness or whether it's in the whether it's in the harness or whether it's in the LLM. Cost per trace, we can check the cost per trace. We can also check the P99s and P50s in terms of the token cost. Output tokens per trace. We can see input tokens, how they are spiking, how they are performing, so that we can do some kind of a remediation in terms of efficiently sending the input tokens, so that the token consumption can be reduced. The latency and tokens are the biggest concerns, but due to reduction in recent costs for in tokens and latency, hopefully this should not be a problem. So yeah, so run types, you can see what the run types are. For example, we can see like for the agent classify intent, and each of these tools, how are they performing.